right, let's go back to this slide, right? So as you can see in B, what we did was after we got the patterns of the voxels, we presented the different stimuli, whether, for example, it's the horizontal lines here or the slanted lines, and asked the device that we had taught the different patterns to predict what it was the person was looking at. And sure enough, it was really good at detecting the patterns of firings in the cortex and correlating that with what the person was actually perceiving. And this is actually really good news if you're doing brain research, right? This means that there is a predictable pattern of activity in the visual cortex that corresponds to, in some way, to the patterns that are being perceived, right? So here's another example where we kind of did this at a very large scale, and we basically presented 1,750 images of different types to a person and recorded the response to a large number of voxels, right? So each voxel, for each voxel, right, we calculated the response of each voxel, right, to each one of the images, right, and we were able to build this model of the pattern or responses of the voxels of the little patches of the visual cortex based on these images to try to predict, to see if there is a pattern between what's being perceived in these images and the pattern of how the voxels are firing, right? So, for example, here's one of the things that we looked at, right? So, we have, and this is from page 118 of your book, right? So if we go to 118, and we had a couple of different decoders, right, that were looking at these images and trying to pick out which image was the one that was being looked at. And we had two different computer models that were used here. We had one that just did structural encoding. In other words, this model simply looked at the tried to pick out the different objects that it found in the image, and then tried to match those objects, the objects that it found, to another image to see which one was the best match, right? Trying to identify it. And it, did okay, right? Not too bad. But then we had another model that did not only structural analysis, and not only did it look at, the pixels and, how they're arranged, right? But it also did a semantic analysis. In other words, this thing would look at a picture and it would try to identify the objects that were sitting in a picture. So it would find building and sky and whatnot. And then what it would try to do is match the image based on the structural information as well as the semantic information. And as you can see, the model that did the matching according to the pixels, right, the objects that it saw, plus the semantic analysis of the words, of describing what was in here, that model did a lot better, as you can see here, at trying to pick out images than just the structural model, right? Just the structural model, for example, it found this stuff, but it kind of confused, this tree, and this rock with this like beach area here, right? Whereas this thing found buildings, and it sort of found this, plaza view, right, of these buildings, right? So it worked pretty well. Another question we have to ask ourselves when we're talking about perceptual areas of the brain is, what is it with faces, right? I mean, we seem to have special areas in our cortex that are devoted just to analyzing faces. We have this fusiform face area that only lights up when faces are presented. The amygdala, which is a part of our limbic system in our brain that has been very strongly associated with emotion and fear, is activated by emotional aspects of faces. So if we see a face that is fearful or threatening, it will elicit an emotional reaction, or it'll elicit an emotional like response in the amygdala. The superior temporal sulcus, right, which is a part of the cortex, right here on the side of your head, um, responds to where you're looking, right, where the person is looking, and to mouth movement. So it seems to be really important in following mouth movements, which are important for perceiving speech. And then finally, the frontal cortex, right, the front part right here, uh, lights up whenever we're evaluating facial attractiveness, right? So if you're looking at somebody and you're evaluating their attractiveness, which we all do, right? That part of the brain seems to be very particularly involved in that. So we have this constellation of different areas of the brain that respond preferentially to different aspects of perceiving other people's faces, right? So for example, here we have we have cars and faces, right? Cars versus face. Now, cars are very familiar objects to us, right? Very familiar objects. Um, and of course, faces are obviously, very important to us as well. And sure enough, whenever we look at the activity, right? The activity of um, whenever we ask people to perceive a car, cars or faces, right? It turns out that it's a lot easier for us to detect upright faces as opposed to inverted faces, right? We tend to make more mistakes in determining if we in fact uh, to match, right? To match faces, right? We do a worse job at matching faces when they're upside down versus when they are inverted, right? Probably because the part of our brain that perceives faces isn't used to perceiving upside down faces, right? It doesn't do a very good job of translating upside down faces. But if I show you a right side up face like this and I ask you which one of the two faces below matches it, you're pretty good at that, right? You're able to say, well, I think this face matches that dude right there, right? But when I turn them upside down, you're not so good at it, right? And that's only with faces, though. With cars, we're okay. I mean, I can tell an upside down car. I can say this car is probably that car. And then I can also say when it's upside down, I can say this car is that car as well. So it's really funny that this inverted task of matching inverted objects is only affects our abilities to perceive faces, right? Which tells us that we do have a separate separate processes in our brain for processing faces that's distinct from processes for processing other things, right? Um, Again, we can work with, how much information do we need, right, to process a face, right? So, obviously, with a full photo, right, we can do pretty well. Uh, so, what's the most important aspect of processing a face? Well, we focus a lot on the eyes, right? In terms of face focus, in terms of trying to identify what a face is, eyes are very important, right? So this experiment looked at our ability to process or identify, I should say, identify faces based on contrast, how much contrast was presented in the picture, right? And this is represented in your book on uh, um, page 120, right? So here's a picture of Newt Gingrich, right? So whenever somebody was shown this image, they were like, oh, I don't know, right? That's kind of hard to say who that is. And only about 50% of the people got the person right. Right. But when we changed his eyes to positive, right? So we put in regular looking eyes, but left the rest of the image negative. The performance went up almost perfect, right? People said, "Oh, that's Newt Gingrich," right? And then, of course, with the full positive image, everybody said, "Oh, yeah, that's Newt Gingrich, who was the former Speaker of the House back in the Reagan years, or back in the Clinton years, I should say." But the point being here that the eyes seem to be very important in our overall ability to perceive faces, right? So here's a picture of these parts of the brain, right? The frontal cortex, and this is looking at a brain, a human brain. This is the front of the brain right here. This is the back of the brain. So this is the back of your head. This is the top of your head here, and this is the side of your head. And the brain is looking in this direction here, so your eyeballs are right about here somewhere. Okay. The frontal cortex is here. It's called frontal for obvious reasons. It's in the front of your head, right? The occipital cortex is our visual cortex. It's in the back of your head. The fusiform gyrus is actually located underneath this fold. If it goes in like that, it's located under there. The superior temporal sulcus is this right here. And then your amygdala this is not your amygdala. Your amygdala is located inside, inside this this part here. It's buried underneath this cortex, but it's right about there. Okay, so these are the brain areas that we're talking about, right? One of the things we want to understand, if we do have this, this unique ability to perceive faces, is how does it develop, right? Where does it come from? And one of the ways we do this is by studying how babies perceive faces, right? Faces are like one, if not the first, then one of the first things that babies perceive in their environments, right? And we think this is how babies kind of see the world, right? As they age, as they get a little bit older, right, their vision comes into clarity, right? So by the time they're 3 months old, if they have normal vision, they should be able to see fairly clearly. And then as they approach a year old, their vision clarifies up a little bit more. But as a newborn, they can't see very far, right? They can really only see about that far, which is just far enough to see mama's face when she's nursing, right? You can measure how interested babies are in things by measuring how long they look at something, right? How long they move their eyes towards something. You can measure that. Even very little babies that are like 3 weeks old, you can measure that. And one of the ways that we're able to tell if they perceive faces is by showing them this like little paddle with a face. They will spend a lot more time looking at that paddle than they will at a blank paddle, and they'll spend slightly more time looking at a face paddle than as they would with all of the different parts of this picture rearranged. So we see that babies at a very young age are interested in faces, and they do spend a lot of time looking at them, right? If we look at the MRI images of a child brain versus a human brain, right, we see here these side-by-side views, right? We see the fusiform area of a child and then the fusiform area of adult, right? The parietal area here, right? And the fusiform face area here in the adult. You can see that the fusiform face area is huge, is much, much greater developed in an adult than it is in a child, right? So children do, or probably, or they do, as we know, right? They have not seen as many faces as adults have. They have not had as much experience perceiving as many different faces, right? So children's ability to perceive faces is going to be relatively limited compared to an adult.